factors, we're going to be getting into some more layers of the OSI model. Specifically, we're going to be talking about IP addressing and IPv6 addressing, and then we're going to take a look at some subnetting. This is the new version of the exam, so subnetting is not as heavily tested on as it was in the past, but it is still something that you guys have to be familiar with. So we're going to spend some time talking about subnetting, and then we'll get into some routing concepts, which will hopefully answer some of those routing questions that you guys had that you were asking about right before the lunch break. Okay? So the network layer. Network layer is layer 3 of the OSI model. And we know that this is where routers function. So a lot of focus is going to be on how routers handle traffic, and of course the addressing component that's utilized at this layer. All right, which is IPv4 or IPv6 addressing. The network layer is an end-to-end layer, meaning that the information that is contained within the network layer can be used to transport data all the way from one end of the network to the other. Now, conversely, when we talked about the data link layer, what was the scope of a data link layer address? What was the scope of a data link layer address? How far did that data link layer address go?
The device that had that MAC address.
Only up to the router. That's what I'm looking for, right? Layer 2 addressing only goes up to a layer 3 device. It doesn't go beyond a layer 3 device. Whereas in layer 3, addressing can go beyond the router or beyond the multiple routers all the way to the end of the network. So we use, this is what we refer to as logical addressing. We use IP addressing to identify end devices as well as to identify intermediary devices like routers in between. Of course, at the network layer, we do have encapsulation. We have encapsulation in the form of an IPv4 header or an IPv6 header. Routing occurs at this layer. And at the other end, when we receive the data, we of course do de-encapsulation, where we remove the layer 3 information before we send the data up the stack. Two protocols that we see at this layer, IPv4 and IPv6. We used to have some other protocols like Novell's Inter-Network Packet Exchange Protocol, or IPX, AppleTalk, and the Connectionless Network Service, or what we refer to as DECnet. But in reality, we only have two protocols that function at this layer, IPv4 and IPv6. So we're going to go take a deep dive into each of these protocols. All right? Very, very, very important chapter, actually. Not so much for the test, but for your general knowledge and general understanding of how routers function and how routers make decisions, right? Now, the characteristics of IP, and by the way, this applies to both IPv4 and IPv6. First of all, IP is what we would consider to be a connectionless protocol. So what does it mean for IP to be connectionless? What is a connection-oriented protocol as opposed to a connectionless protocol? Any ideas? Any ideas at all? A connection-oriented protocol means that it is a protocol that establishes communication prior to sending or receiving information. Now in IP, we don't do that. In IP, I simply send my datagrams out. If they get to the destination, they get there. If they don't get there, they don't get there. But there's nothing within an IP header that allows me to establish that the destination exists or that the destination is available prior to sending my information. That's why we refer to IP as connectionless. No connection is established prior to sending the information. It's also best effort, meaning that we don't have any guaranteed delivery of the datagrams. See, when we talk about layer 4 later on, we're going to talk about a protocol called TCP. And within TCP, we have a function of TCP that ensures that data has been delivered to its appropriate destination. That is what we call sequencing and acknowledgements. We do not have that function inside of IP, so there's no guaranteed delivery. If the datagram does not arrive at its destination, there's no way to identify that, all right? Also, IP is completely media independent, meaning we don't care what the transport is. We don't care what the physical layer is. IP functions the same regardless of whatever the physical transport is. The data link layer is not like that, right? The data link layer has different encapsulation methods for different types of transports. Serial connections, for example, can't run Ethernet. But we can run IP over serial, and we can run IP over Ethernet. Does that make sense? So at the data link layer, we do have some dependence on the physical layer based on what protocol we're going to run for that particular physical layer construct. But in IP, it doesn't matter. Okay? So here we go. What we're seeing in this particular slide here is what we have. Well, it's an IP header. Okay? IPv4 packet header. Now, prior to getting into some of the iOS stuff, we talked about data link layer, right? And we talked specifically about an Ethernet header. Do you guys remember what the format of an Ethernet header was? What was the format of our Ethernet header? What was the first field in an Ethernet 2 header? You guys remember? I'll give you a hint.
Preamble.
Well, the preamble, yes, the preamble comes first, but it's not really considered a field because it doesn't contain any relevant information that allows us to process the frame. Remember what the preamble was used for? It's just used to indicate that something is coming, right? So technically, the first field that actually holds information that is used, destination MAC address, right? The second field was source MAC, right? And then the third field was the type field. And that is the extent of a layer 2 header. Only 3 fields in a layer 2 header. The destination MAC, the source MAC, and the type field. You guys remember that? Okay? All right. So, as you can see, an IP header is far more complex than a data link layer header. But just like the data link layer header, we're going to spend some time breaking down each component of this header. Let's start with the version field. Now, we already talked about this, right? There are 2 versions of IP, IPv4 and IPv6. This is a 4-bit field. You guys see that, right? The first byte is split into 2 pieces. You see that? You guys agree with that, right? So the version field is a 4-bit field. If it's IPv4, this field is going to be 0, 1, 0, 0. You guys agree with that? Why would it be 0, 1, 0, 0 if it's IPv4? Because that's the numerical value. That is the binary string that represents 4 in decimal, isn't it? Remember, it's 1248. 1248. So the first 0 represents a decimal 1. The second 0 represents a decimal 2. The third 0 represents a decimal 4. And the fourth 0 represents, or the third 1 represents a decimal 4. And the fourth 0 represents a decimal 8. Make sense? So what if it was IPv6? what would the value of that first field be if this was an IPv6 header and not an IPv4 header?
0110.
0110, that's right. It would be 0110. Okay? Now you don't need to know that for the test, but you know, it's not just, this class is not just about understanding what's on the exam. It's about being able to understand what the hell you're doing at work and what the hell you're doing with networks and how you can look at packet headers and captures and identify what's happening with a packet and how the router's interpreting that information, etc., etc., etc. Now the second field that we see is called the header length field. You will only see a header length field if that particular header can change in size. Now a standard IPv4 header, as you can see on the right side of the diagram, is 20 bytes. So if we're using a standard header, the header length field will indicate that this is a 20 byte header. We do have some options, and we do have some padding bits that we can set. So by setting options and setting padding bits, we can go beyond 20 bytes, which means that that header length field will indicate that the header is a non-standard D4 header. So that's all that field is used to represent. It's used to represent whether a header is standard 20 bytes or if it goes beyond the standard 20 byte length. All right. So first field we talked about, the version field, we're good to go on that. Second field we talked about. What about the third field? The third field is an entire byte. Traditionally, this was called the TOS byte, TOS. This was traditionally called the TOS byte. And that TOS stands for type of service. Now what this field is used for, it's really kind of beyond the scope of this class, but what this field was used for, it was used for quality of service. More specifically, this field is used to mark packets with a number so that routers that are processing this packet header can apply a QoS policy to those packets. It's kind of like going to the post office and you can get, if you want to mail something from the post office, you can get different types of envelopes for different types of mail. You can get priority envelopes for priority mail processing. You can get a media envelope for media mail processing. You can get an express envelope for express mail processing. So what this field allows us to do is mark the packet with a number. And that number is called a differentiated services code point. That's what DSCP stands for, differentiated services code point. And what that number then does is allow the router to interpret that number and then apply a quality of service process to that packet. Okay? Now eventually we're going to start to add some quality of service to the material here. We haven't quite done that yet. You might see a couple of QoS questions on the test. For now, you're going to have to memorize those, but in the future we'll have some QoS stuff on the exam or on the material. But just know that by default, this field is set to all zeros. Okay? By default, DSCP is not used. So you should see all zeros in this entire field. We've got ECN bits as well. There's 2 of those. The ECN bits are called explicit congestion notification. It's also another QoS property that we can set and so on. Okay? In QoS, we have a couple of different things that we can do. We can queue packets. We can prioritize packets. We can police packets. So I'll mention that since that's the one question that's on the test. When you're policing data, you're setting a threshold for that data, and it's typically related to bandwidth. And if you exceed that threshold, that data that exceeds the threshold gets dropped. That's what policing does. Shaping doesn't drop the exceeded data, it queues the exceeded data, or it buffers the exceeded data. So shaping is a little bit less aggressive, but it still kind of manipulates or manages bandwidth. All right. The next field that we have is something called the total length field. It's a 16-bit field, and it's very simple. The total length represents how much data is encapsulated above layer 3. In other words, what is the payload? We're going to use that term quite a bit, payload. Payload simply refers to what's being carried. You know, we see the term payload all the time. We'll talk about payload if we talk about GRE. GRE is an encapsulation protocol that allows us to encapsulate routing packets. And those routing packets are the payload. In layer 2, the data field, which is that field that goes from 46 bytes to 1500 bytes, that's my payload. In layer 3, everything that goes above layer 3, which follows the layer 3 header, is my payload. So the total length field tells me how much data is actually encapsulated. But one thing I want to point out, that total length field includes the header itself. So if I have a total length of 420 bytes, and I'm using a standard IPv4 header, how much data is actually encapsulated above IP?
Above?
This is IP, right? This is an IP header. When I say above IP, I mean what comes after layer 3. So if I have a total length field of 420 bytes, and I'm using a standard IPv4 header, how much data is being carried above IP? Well, if a standard IP header is 20 bytes, and the total length field includes the header, 400 bytes, yes. Okay? You guys have to think about encapsulation is kind of like nesting dolls. You guys know what those Russian nesting dolls are? Where you have like one doll inside of another doll, inside of another doll, inside of another doll. Each header is the outside doll. So when you open up that doll, what's inside is the payload. So you've got your outside doll, that's the layer 2 header. You open that up and guess what you see? The layer 3 header. You open that up, what do you see? The layer 4 header. You open that up, you see the layer 5 header. Eventually you get to the actual raw data. But from a router's perspective, everything above layer 3 is data. Because what layer do routers function at? What layer do routers function at? 3. Do routers care about layer 4? Do they care about layer 5? Do they care about layer 6?
Not really.
No. So everything above layer 3 from a router's perspective is simply data. You guys follow what I'm saying? Everything above layer 3 from a router's perspective is simply data. The router could care less what happens above layer 3. Okay? All right. The next 3 fields, they're all kind of directly related to each other. We have identification, we have flag, and we have fragment offset. We're not going to spend too much time talking about these 3 fields. These 3 fields simply represent whether or not packet fragmentation is going to occur. And quite simply, fragmentation is an extension of segmentation. Now, what layer did segmentation occur at? We talked about that yesterday. Segmentation is the process of what? Segmentation is the process of what? ideas. What is segmentation? It was like the third or fourth slide we talked about. Breaking up data. Right. Remember we talked about the MTU, we talked about 1,500 bytes is the maximum amount of data that we can encapsulate in layer 2. And segmentation is the process of taking large amounts of data and dividing it up into smaller pieces so that everybody can get access to network resources, right? You and I had a very specific discussion about segmentation. We talked about what multiplexing was. We talked about if I'm sending large amounts of data and you're sending small amounts of data, how can I ensure that you're not going to get starved out from my conversation? But because I divide my data up into smaller pieces. Now, do you remember what layer is responsible for doing that? What layer is responsible for doing segmentation?
Transport layer?
The transport layer, yes. Specifically TCP and UDP. Now the transport layer is layer 4, right? So there may be instances where data has to be further divided up, but we can't do that at layer 4 because the only devices that understand layer 4 are the hosts themselves. Routers don't understand layer 4 because routers operate at layer 3. So we have something called fragmentation. Fragmentation is to layer 3 what segmentation is to layer 4. It allows the router to divide data up into smaller pieces based on MTU as necessary. So the identification field, the flag fields, the fragment offset field, those are all used in the event that packet fragmentation has to occur. All right, that's really all we need to know about those 3 fields. That's the downside of having a smaller class, is when I ask questions, there's only 2 people that I get to look at to answer the question. All right, if I had 10 or 15 people, you could just stay quiet and somebody else would probably answer. But not in this case, one of you 2 have to answer. Which means I get to be mean to you guys instead of somebody else. All right? I know it's a lot of information. We haven't even scratched the surface yet, trust me. But I assure you that you will retain more than you think you will once you leave this class. You're not going to remember everything. There's no way. That's why all of our students can resit our class as many times as they want for 24 months for free. Because we know that every time you take the class, you learn something else, right? Okay? That's something new that we're doing. So now you can come back for the next 2 years and sit as many times as you want. Okay? All right. The time to live field. Now this field is relatively important. It's called the time to live field. It's an 8-bit field, which means that numerically it has a value from anywhere, a decimal value, from 0 to 255. Okay? Because it's an 8-bit field, that's essentially what it means. I have a numerical value from 0 to 255, a decimal value. Okay? Now what the time to live field is used for is it's used to define the lifetime of a packet. The lifetime of a packet. So here's how it works. If I have a device generating a datagram, I generate a packet, I set that time to live value to a number. Let's say I set it to 10. Okay? every time this packet passes through a router, in other words, goes in one interface and goes out the other interface, that value gets decremented by 1. So it goes through you, it goes to 9, it goes through you, it goes to 8. If that value reaches 0, the packet is destroyed. So it identifies essentially the lifetime of a packet. The time to live field allows us to identify the lifetime of a packet. The idea being that if a packet gets caught on the internet or caught in the network in a loop, that it won't stay on the network or the internet forever and keep going around and around. Eventually, the time to live value will reach 0 and the packet will be destroyed. Now, Cisco devices will set that time to live value at its maximum, which is 255. So that means that it can go through 254 routers successfully, but if it tries to go through a 255th router, it will be destroyed. Other operating systems, other computer systems will set different values. I think Windows uses a time to live of 128 by default. All right. Now, the only device that can manipulate that field is a layer 3 device, because this is a layer 3 header. So switches do not modify the time to live, because switches operate at layer 2. A switch does not look at a packet header. There's nothing in a packet header that a switch needs to look at. Geo says, time to live reminds me of DDoS attacks. Yeah, well, I suppose. I mean, if we can manipulate that value somehow, we can, of course, modify the scope of a packet, but yeah. The time to live cannot exceed 0. All right? Protocol field. The protocol field. Now, at layer 2, here comes another question, guys. At layer 2, we had a field called the type field. It was the third field in my data link layer header, my Ethernet 2 header, was a type field. Do you guys remember what the type field was used for? What was the type field? What was the purpose of the type field? Any ideas? The type field allowed me to identify what the next header was. I'm beginning to wonder if people were here yesterday. The type field identifies, is the next header IP? Is the next header ARC? Is the next header IPv6? Is the next header ICMP, etc. Okay? The protocol field is the same thing for IP, but it allows us to identify what comes after layer 3. So you might see a protocol of TCP. You might see a protocol of UDP. You might see a protocol of EIGRP. You might see a protocol of OSPF. It just depends on what comes after the IP header. You have to remember, guys, that these devices that are processing these datagrams, they need to process all of the data. So if it's EIGRP that comes after the IP header, then the router says, you know what, I probably need to look at that because I'm an EIGRP router. If it's TCP that comes after the IP header, the router probably says, you know what, I don't need to look at that because I'm not a layer 4 device, I'm a layer 3 device. So I'm going to allow the host to look at that information. Every single layer has a reference to the next layer. At layer 2, the type field is used to represent what comes after layer 2. At layer 3, the protocol field is used to identify what comes after layer 3. At layer 4, the port field is used to identify what comes after layer 4. So every layer has a hook or a pointer to the next layer. All of a sudden, that Ethernet header is looking a lot simpler. Oh, we've dropped a bunch of people. Let me see if I'm still online here. Juan, can you still hear me? It's really strange that like more than half the people dropped off. The internet's still working. Okay, well, maybe Europe is having a problem with their internet. I don't know. Or maybe people decided to go to eat dinner or something. All right, the next field is called the checksum field. It's a way for us to verify the integrity of the header. It's like a hash, just like we saw with layer 2 with the CRC. A checksum field allows us to identify the integrity of the hash or the integrity of the header itself. protocol ID of 89, etc. Lots and lots of different protocols have different protocol IDs. You all right over there, Bernard? Yep. Okay. Checksum. That's the checksum, but we've validation is disabled, meaning that the routers along the path don't actually have to verify the checksum. This is the number that we came up with. Of course, that is a 30 or 16-bit number. The source IP is 165. The destination IP is 125.
So what tells it that the checksum is disabled?
Part of the flags. Some of the flag settings. We see the flags are marked as hex 02. That means that we're not fragmenting and we're not verifying the checksum. Okay. All right. So the idea here, guys, is that you can open up a Wireshark application, and if you're tasked with troubleshooting a network, or you're tasked with understanding, based on a capture, what's happening with a particular packet, you can use this information because you now understand what each of these fields represent. You can say, well, this is a voice packet. It's supposed to be marked DSCP-EF, but I can tell it's not marked EF because I can see the DSCP value is 00. So you can troubleshoot that. You could say, well, why is this packet not being marked EF? And we can find out, potentially where that might be. The packet's getting dropped after the third hop. Well, if the time to live value is only 2, then the packet would get dropped after the third hop. Actually, before the third hop. So you can look at certain aspects here and make assumptions and decisions based on what you're seeing here about how data is going to be handled. And that's why this is so important. Now, as if that wasn't enough, what about IPv6? We talked about IPv6, even though it's kind of been removed from the exam. I'm not sure why they did. They used to have IPv6 heavy on the exam, but we're still going to talk about it because I love IPv6. I think IPv6 is wonderful, and it's something that's exciting, something you guys are going to be exposed to over time. First of all, everybody kind of knows this, right? IPv6 addresses are 4 times the length of a v4 address, so it's going to give us a lot more address space. All right? But there are a lot of other things about IPv6 that make it much, much better. The header is actually a lot less complicated. The v6 header is much less complicated. All right? All IPv6 addresses are public. At least all the ones we use for our clients are public. So we don't have this need for NAT. We don't have this need for private addressing. We'll talk more about private addressing in the next chapter. IPv6 has built-in security. AH and ESP are built into the protocol. AH stands for authentication. ESP is encryption. Actually, E stands for encapsulation, but it's basically encryption. So IPsec is built into IPv6. And no more broadcasting in IPv6 either. Over 4 billion addresses in IPv4, but over 340 undecillion addresses in IPv6. So clearly, a lot more space in IPv6. All right. So let's talk about the header. On the left, we see our IPv4 header. Those are all the fields we talked about, the version field, the header length field, type of service, total length, etc. These are all the fields that we talked about in IPv4. But all of those red squares that you see there, all the dark ones on your page there, those are all eliminated in IPv6. No more packet fragmentation in IPv6. No more header length field because an IPv6 header is fixed in length. It's 40 bytes, period. No exception, 40 bytes. Okay? The yellow fields, or the yellow, orangish fields, whatever, these are the fields that remain the same. Destination address, source address, header, version field. And then the blue fields, the navy blue fields, those are the same, but they were just renamed. So traffic class was type of service. Traffic class was type of service, so that's used for QoS. Payload length was total length. So in IPv6, we don't care about the header. We're only identifying the payload size, which makes sense because the header's fixed. I don't care about the header length anymore because the header is fixed in length. Next header is my protocol field, and the hop limit is my time to live field. All of those blue fields do exactly the same thing as they did in the v4 header. Okay? So actually, by kind of spending a lot of time and talking about each of the individual components of the v4 header, you have a pretty good understanding of what the v6 header does. The only new header that we have in v6 is something called the flow label field. That flow label field is 20 bytes in length, and it's used for, it's actually, or 20 bits, excuse me, not 20 bytes. That would be over half the size of my header, right? 20 bits in length, and it's used for identifying other QoS type of characteristics. We're not going to really get into the flow label field. All right. So this is what my v6 header looks like in Wireshark. Pretty much the same thing. I've got my version field, 0110, makes sense because that's v6. Traffic class, my 6 bits for DSCP plus my 2 bits for what? My 6 bits for DSCP plus my 2 bits for ECN. I've got my flow label field, which is 20 bits. Right? 4, 8, 12, 16, 20. My payload length, 36 bytes. That means that there's 36 bytes of data carried inside of IP. Remember, that payload length field does not include the header length like it did in IPv4. The next header, in this case, is an extension header. Extension headers are kind of beyond the scope of this class. I could see next header as TCP or UDP here as well. In this case, this is a hop-by-hop option extension header, so that's what follows the IP header. Hop limit is 1. Okay, well that's interesting. That means that the scope of this packet is only to the next router. It can't even go beyond the next router. Because if it tries to go beyond the next router, that hop limit value gets decremented by 1, and the packet gets destroyed. Source address, destination address. Of course, the addressing is completely different. Here we see a bunch of weird numbers and letters for our addresses. But we're going to learn about that in the next couple of slides. Okay? So actually, that's where you see destination. That's really where the header ends, where you see destination. All the rest of that stuff after that is the next header. Okay? All right. We're going to get into some more detail about that a little bit later on, but let's go ahead and switch gears a little bit, and let's talk about routing. Because we are talking about layer 3, aren't we? And the responsibility of a router is to forward data to its destination. That is the responsibility of a router. So routers have interfaces. How many interfaces are attached to this particular router?
3.
3. Okay? So that means that this router is attached to how many subnets?
2.
If it has 3 interfaces, it's attached to 3 subnets. There's no exception to that rule. You cannot have the same subnet on 2 different interfaces on a router. If a router has 5 interfaces, it has 5 subnets. If a router has 20 interfaces, it has 20 subnets. Period. Okay? A subnet is a network, right? A subnet is a network. 3 interfaces, 3 different networks. You guys got me? Now, what is the goal of a router in general? To take a packet from a host on one network and to be able to route that packet to another host on another network. You guys agree with that? So let's say, for example, I've got a PC over here on the 10 subnet. So here's my PC on the 10 subnet. I've got a PC over here on the 10.1.1 subnet. The goal of, if this PC wants to talk to this PC, the goal of this router is to be able to take that packet from that host on the 10 subnet and send it along towards its destination. You guys agree with that? What are switching? Yep. The squares are switches, the circles are routers. All right. When it comes to routing, though, there's some very important things that you guys have to understand. What does a switch do when it doesn't know how to reach a host? What does the switch do? It floods, right? It sends the frame out of every port except for the port it came in on. Agreed? Routers don't do that. Routers do the opposite. If a router does not know how to reach a destination, it drops the packet. So routers only do what they're told to do. They don't have any default action. A router by default doesn't really know anything. It has to be told how to reach destinations. Now, naturally speaking, router 1 has 3 interfaces, yes? So wouldn't it be safe to say that router 1 should at least know how to reach 3 networks? How many networks exist in this topology altogether? How many networks exist in this topology?
5.
There are 5. Forget those circles. There are 5 networks. You've got 5 separate interfaces, right? You've got 1, 2, 3, 4, 5. 5 interfaces, 5 networks. One network is shared by both routers. You guys agree with that? So, the goal of a router, as I mentioned before, is to take the packet coming in on one interface and switch that packet or route that packet to another interface. That's what routing is. What does a router look at to make that decision? What does the switch look at to make a forwarding decision?
The
Destination MAC address, right. What does a router look at to make a forwarding decision?
destination IP.
Destination IP address. That's right. Switches have a MAC address table that's built. Routers have a routing table that's built. I'm building up here. I'm trying to bring you guys along here. Now, the routes that show up automatically are what we call directly connected routes. What do you think a directly connected route would be? What do you think a directly connected route would be? Just by its name, what would a directly connected route be?
Something physically connected to that router, or?
It's a network that's physically attached to the router. Absolutely. How many directly connected networks exist on router 1? 3. You guys see that? How many directly connected networks exist on router 2? 3. Okay?
Can I ask a question there?
Sure.
Because let's say router 2 is in China and router 1 is in DC.
Doesn't matter. Go ahead, but doesn't matter.
I mean, theoretically, you might have 10 other routers in between those two.
Not based on this topology. Based on this topology, these routers are connected with a serial link. That is not a cloud in the middle. That is a point-to-point serial link. Okay? Theoretically, we could have all kinds of network designs, but that's not what we're seeing in this particular slide. Now, we're going to talk about other technologies like layer 2 VPNs, MPLS, DMVPN. We've added those topics to this course, where the cloud in between has a bunch of routers inside of it, but oftentimes that cloud is still transparent. Okay? I'm not going to get into that right now, though, because our goal for right now is for you guys to understand the fundamentals of routing. Then we'll add some of the advanced concepts later on. Now, I'm asking all these questions because out of everything that you take away from this class, routing is probably one of the most important concepts. That's what you're going to be exposed to the most. That's what most people have the biggest difficulty with. Setting up VLANs, setting up spanning trees, setting up BTP. Yeah, there's some complications to that, but it's generally fairly easy. Routing, on the other hand, can be very difficult. Okay? So, the goal of a router is always, regardless of how the routes are learned, the goal of a router is to take a packet and get it to the next router. There could be 500 routers in this link. Of course, that wouldn't work because our time to live, but there could be 50 routers in this link. The goal of any router is to always get the packet to the next router. That's it. It doesn't matter if it's EIGRP, OSPF, BGP, static routing, default routing. The goal is always, who is the next router I send the packet to? See, if I want to send a packet to somebody attached to you, and he's in between, I don't really care about technically how I get to you. I just need to know I need to go to him to get there. So I send the packet to him, then he sends the packet to you. Does that make sense? Routing is always about who's the next router. We call that the next hop. The next hop. So R1, in order for R1 to reach the 10.1.1.0 subnet, the next hop is R2. Agreed? In order for R2 to reach the 192.168.10 subnet, the next hop is R1. Does that make sense? Now, naturally, in order for R1 to reach R2, don't the connected networks have to be there first? In order for R1 to be able to reach R2, don't the connected networks have to be there first?
You mean the switch connection?
In order for R1 to be able to get to R2, don't the connected networks have to be there first? What is a connected network? We just defined it 3 minutes ago. No, a connected network is a network that's attached to the router. A connected network is a network that is attached to the router. R1 has 3 connected networks. R2 has 3 connected networks. Do you guys agree?
Yes.
All right. So I'll ask the question again. What do you mean you disagree with that?
Because the networks on router 1 have to connect, so obviously the packets have to go to the router, but it doesn't need to be connected on router 2 because.
That wasn't my question. My question was, in order for R1 to be able to get to R2,
Yes. Right.
don't the connected networks have to exist first? I'm talking about specifically with this topology.
Okay.
How does R1, excuse me. Excuse me. How does R1 get to R2?
By one connection.
By a connected network, right? By this serial link. So there's a reason I'm asking this. I don't know why Cliff's stuff keeps unmuting. I have to keep muting him. Okay. The reason I'm asking this is because I want you guys to think about the process, because when we're configuring routing in our network, there's a procedure you have to follow in order to ensure that routing is going to work correctly. The first thing you have to do is you have to make sure that those connected routes show up. Because if the connected routes don't show up, then you're never going to be able to get to anything beyond that route. Does that make sense?
Yes.
Cliff agrees. Okay? So that's what they're talking about in this slide. R1 has 3 directly connected networks, 10.0, 11.0, and the 224 subnet. R1 has 2 remote networks, but before R1 can even think about reaching those remote networks, this serial link has to be active and the router needs to know it exists, right? How does that happen? That's a rhetorical question. The way these connected networks show up is very simple. You put the IP address on the interfaces and you make sure that the interfaces are operational. That's it. There's nothing you actually have to configure for the connected routes to show up other than making sure that the interfaces are on. That make sense? And that they have their IP address. Now, of course, we have to have a way for router 1 to be able to reach the 10.1.1 subnet. We have to have a way for router 1 to be able to reach the 10.1.2 subnet. That gets a little bit more complicated, doesn't it? Because those networks are not connected. And I think that's what you were kind of alluding to previously, right? Saying that, well, not every network can be connected to router 1. There are some networks that are not going to be attached. And quite honestly, there's probably going to be a lot more networks not attached than there are attached. All right? But here's the bottom line. We'll move on from this slide. The bottom line is when you're setting up routing, regardless of however routing is occurring in your network, when you're setting up routing, the very first routes that you want to verify are those connected routes. Because without those connected routes, nothing else will work. Do you guys agree with that? Okay? So, as I mentioned before as well, the goal of a router is to always send the packet to the next router. The goal of a router is to always send the packet to the next router. So here's an example where I might have multiple routers in between. I've got a network on the left, I've got a network on the right. Now R1 has 2 connected subnets, but there are also 2 other networks that are not connected. So in order for R1 to be able to route to the 4 subnet, which is the one on the right, it's going to have to learn about that subnet. The packet's going to come into R1. R1's going to do a lookup and say, oh, I need to send the packet to R2. Once R1 sends the packet to R2, R1 is done. It's done its job. It's sent the packet along towards its destination. It's then up to R2 to make a decision. R2, of course, will send to R3, and so on.
I just have a question about, maybe it's terminology, I'm not sure, because, I mean, I know what we're doing here,
Yeah,
but, you said that R1, if it doesn't know about that 4.10 network, it's going to send to R2.
no, if it doesn't know, it drops it. Routers do not route packets unless they know how to reach a destination. If a router does not know how to reach a destination, that packet stops there. Now, the 4 subnet's not connected, so R1 is going to have to learn about that 4 subnet through some other method. We haven't talked about that yet. But assuming that we've configured everything correctly, R1 should know about the 4 subnet because it learned it through some routing process. But routers do not route packets unless they specifically know how to reach a destination. Unlike a switch that will flood frames, routers do not do that. They will only route packets if they know how to reach a destination. Did that answer your question? Not convinced.
No, I mean, but I'm just trying to think, because if I'm trying to get from here to some resource that's in China, well, I'm just using China as an example, then somehow the first router I hit from wherever I'm sitting at my house or this classroom
Right.
has to know something about routers all the way from here to there.
Not necessarily. Does a host or does a PC know how to reach China? Does your PC know how to reach China? You can probably open up your browser and go to some website in China right now, but does your PC know how to reach that network?
No.
What does it use to get there?
It's going to probably create a TCP connection before it can send out.
Well, the only way to create a TCP connection is to have IP, because TCP is above IP. So IP has to come first. How does that PC know how to reach a destination in China? There's something that's configured on that PC that allows that PC to reach China.
The gateway.
A gateway. What is the purpose of a gateway? If you don't know how to get there, send the packet here. Which means that the PC will be able to reach anybody because it goes to the gateway. Now, what is the gateway? The gateway is the router. Well, guess what? There's a special type of route called a default route, which matches any destination. And say from this hotel, the hotel's not going to have a route to every single destination on the internet, but the hotel is going to have a default route that points to the service provider. So even though the router might not specifically know how to reach the rest of the world, it's going to say, well, I'm just going to send this packet to my ISP, and then I'm going to let my ISP handle how to route that packet. Will the ISP know how to get to that route in China? It depends what kind of ISP it is. If it's a tier 1 ISP, most likely, because they have really, really expensive routers with millions of routes in them. If it's a local carrier that maybe a tier 3 ISP, they might not know how to get to that specific address, but guess what they have? They have a default route to a tier 2 ISP. And then the tier 2 ISP has a default route to the tier 1 ISP. But eventually you're going to get to somebody that knows how to reach that particular destination.
See, I think that's what's throwing me off, because, I mean, I know that that's how it works, but when we're saying that if the router doesn't know, it's just going to drop the packet.
Yeah, well, any router that has a default route will never drop a packet. But that default route doesn't exist by default. You have to program that default route. It's another form of routing. There are 3 forms of routing that exist: static routes, default routes, and dynamic routes. Okay? A static route is where you tell the router how to reach a destination. Okay? But remember, that static route only points to the next router. No router knows, or may know, but it doesn't make this decision. No router chooses the entire path. The router at this hotel does not choose the entire path to get to China. The whole goal of a router is where do I send the packet to next? That's it. Once that packet goes to the next router, it's up to that device then to decide where to send it. All right? So a default route is a type of route. It is. It's just a generic route that matches everything that wasn't matched by the specific routes. But that default route still allows me to route the packet. Now, does it mean it's going to get to the destination? No, but I guarantee what it does mean, it's not going to get dropped by me. It might get dropped by the next router, but it's not going to get dropped by me. Make sense?
Yes.
Okay? You pull a router out of the box, you configure the interfaces. The only routes that show up are the connected routes. There's no default route, no static routes, no dynamic routing. So that means by default, routers don't know how to route. So you have to program that router to learn how to route. All right? Let's see, we got a question here. Default route is done on the border gateway. It could be, yeah. It's typically done at the edge of your network. A default route is usually on the edge router, but default routes can exist further down the line. It depends on who you're connected to, but there is a structure to the internet. And that structure is a tiered structure. There are about 15 or 16 service providers that make up the backbone of the internet.
That's you.
Okay? Those are called tier 1 service providers. They have multi-million-dollar routers that have massive amounts of memory and millions of routes in them. So they know how to reach everything in the world. Okay? There's probably about 2 million different destinations in the world right now in IPv4. Those tier 1 providers have relationships with each other. They share information about the networks they own and the sub-networks they own and everything else. And then you have tier 2 providers, then you have tier 3 providers. Most likely we're connected at this hotel to probably a tier 2 provider. Okay? But there's relationships that these guys have, and they share information. If they're not sharing information, they have a default route. Now, the router that's at this hotel is a very cheap router. It's a very small router. It doesn't have a lot of memory. And usually there's only one way in and one way out of this location. It's kind of like the router at your house. You only have one connection. So there's no need to have any routes. What do you need? One route, the default route. Because you're going to say, well, I don't care what the destination is. Every single time I try to reach somebody outside of my house, it's going to go to the same place. So I'm just going to have a default route that points to that place. It's like a default gateway for a router. Right? Your PC doesn't know how to reach every single destination on the internet, but it doesn't need to because it has a default gateway. All right? All right. We're just scratching the surface of routing, by the way. We're going to talk about default routes. We're going to look at how to program default routes. We're going to look at static routing. We're going to look at dynamic routing. There's a bunch of stuff that we're going to be talking about with regard to routing. But right now, we're going to take our afternoon break. It's 2:50, 15 minutes.